afternoon. Today, I'm Saritha Kumari, Assistant Professor in EEE Department, working at Institute of Aeronautical Engineering College, Dundigal, Hyderabad. So today the topic is inductance of single phase transmission line. That means single phase two-wire line. Yesterday, last class, I have explained the flux linkages. Um, Flux linkages due to internal flux. That means internal flux linkages. Yesterday I explained. So if we recall, the expression for that is given by, so the flux linkages psi. So internal flux linkages. So mu naught I by 8 pi. Okay. So this is the expression. In my previous lecture, the derivation, I explained internal flux linkages. So now continuation. Now we see the external flux linkages expression. Then we add both internal flux linkages and external flux linkages to get the total flux linkages. Then finally we get the inductance expression. So look here, the conductor, there is a conductor whose radius is smaller, and we consider there are 2 points as it is mentioned here. There are 2 points PQ which are considered externally to the conductor, whose distances are D1 and D2. So outside the conductor there is a point P which is at a distance of D1 meters, and another point Q which is at a distance of D2. Now the flux lines, we know that magnetic flux lines in the form of concentric circles around the conductor. So the magnetic field intensity at a particular distance x meters is given as like this. So which is considered between the 2 points P and Q. So the magnetic field intensity at a distance x meters, it is denoted with h suffix x, which is given by I by 2 pi x. So I by, it is outside the conductor considered. So it is given as the expression magnetic field intensity I by 2 pi x. Okay. So x is the distance we have taken. So ampere turn meter. Then magnetic flux density Bx is given by, because B is equal to mu naught mu r h. So here mu r is 1 because we are talking about the transmission line for in the air. This mu r relative permeability value is 1. So then B is equal to mu naught into hx I by 2 pi x. Then after this, the flux lines is given by d pi is given by, because B is equal to flux by area of cross section. So if we considered a small elemental length dx, so the flux is given by B into A, so which is given by the area is given by, written as dx into 1. 1 is nothing but considered 1 meter length. Conductor length is per meter length, so it becomes 1. So this is the area of the cross section. So this is the flux. So after this flux, the flux linkages is given by, flux into number of turns. So anyway, one conductor, we are talking about one conductor. So d pi into 1. So finally the flux is given, the flux linkages is nothing but flux, which is nothing but bx into tx. Now uh, we consider this is with respect to a small elemental length dx. Now the total flux linkages, which are external flux linkages, right? So is nothing but integral of d pi, integral of d psi. So this is the total external flux linkages. Okay, so here the limits are taken. Okay, what are the limits? External we are interested in points d1 and d2. So what is the expression we get here? Mu naught I by 2 pi log d2 by d1. Okay, so that is the expression we get. Okay, substituted here the d psi. So the limits are the 2 points we have taken, distances d1 and d2 externally we have taken. So the lower limit and upper limit apply. So we will get it as finally mu naught I by 2 pi into log d2 by d1. So that is what here directly we can see the inductance. So the external flux linkages is given by mu naught I by 2 pi log base C, right? d2 by d1, d2 by d1. So now L is given by, so what is the inductance? Ratio of flux linkages to the current. So mu naught into I by 2 pi into I gets cancelled. Finally external, that means the inductance due to external flux. So that means here we have taken 2 points externally. So mu naught by 2 pi into log of d2 by d1 henries per meter. So per meter length we have taken we have taken conductor. So that's why it is units henries per meter length. Now finally if we substitute this mu naught value here, what is the mu naught value? We know that. So 4 pi into, that is a standard fixed value, 4 pi into 10 power minus 7. So it gets cancelled with 2 pi becomes 2 into 10 power minus 7 log of d2 by d1. So these are the this is the inductance due to external flux, where we have taken externally 2 points, okay, PQ, which are at a distance of d2 and d1 and d2. So then this is the expression. So from this knowledge we come to our actual case where the here we can see here it is mentioned as um, we consider the d1 is equal to r1 and d2 is equal to d. That means what? D2 is nothing but distance between the two conductors. In a single phase transmission line, we have two conductors. So the distance between those two conductors is capital D. Okay. Then, then that is a maximum value. Taken it as equal to D2, and D1 is a R actually. So that is nothing but what? That is a radius of the first conductor. So now if we applied in the previous expression, so mu naught I by 2 pi into log of d2. What is d2? Capital D. That is equal to the distance between the two conductors in a single phase transmission line, and down we have R. Actually, here just to understand that this is nothing but the radius of the first conductor. radius of the first conductor. That is a minimum value. Of course, it is shown here R1, but uh, please know that it is same as the uh, radius of the first conductor. So this is R or R1. Okay. Now, if we substitute mu naught, its value is 2 into 10 power minus 7 log of d by R1 into I. Now, the total flux linkages is given by sum of the internal flux and external flux. So, psi is equal to psi internal plus psi external. Okay. Total flux, that is psi, is given by internal flux and external flux. So we know that internal flux already. I hope you remember internal flux is given by mu naught I by 8 pi. So if you substitute for mu naught, it becomes uh, 1 by 2, right? So mu naught by 8 pi becomes 1 by 2 into 10 power minus 7 into I, and then psi external is 2 into 10 power minus 7 I into log of d by r. Okay, r or r1, both are, as I mentioned, both are same here. Now in both, take 2 into 10 power minus 7 is common. 2 into 10 power minus 7 into I, then what it will become? Then it becomes, first term becomes 1 by 4 plus second one becomes log of d by r1. Then this log of 1 by 4 can be written as log of log base e, okay, log base e power 1 by 4, right? So this is nothing but same as 1 by 4 log e. So that is the meaning. So this value is 1. So that's why it is written as log e power 1 by 4. So log a plus log b is what? Log ab, uh, log ab, right? So um, so log of d log a plus log b is log ab. So what it will become? Log of d e power 1 by 4 by r. Okay, r1. So this, okay, this one, so get this e power 1 by 4 down, what it will become? D by r1 into e power minus 1 by 4. Okay, so then this is calculated, whose value is calculated e power minus 1 by 4, 0.7788 r1. So finally this whole term is considered as r dash. Okay, or r1 dash. Okay, so what this is the expression for the total flux linkages. 2 into 10 power minus 7 into log of capital D by r dash. Okay, or r1 dash. So where r dash is equal to 0.7788 into r. Okay, now finally write down the inductance expression from this. So we know that inductance is given by flux linkages by current. So what we will get? So here I gets cancelled. 2 into 10 power minus 7 into log of capital D by r dash, r1 dash. Okay, so this is a expression, final expression for the inductance, okay, of a one conductor. Okay, inductance of a conductor is given by, this is one conductor. Okay, 2 into 10 power minus 7 log of capital D by r dash. Okay, where r dash is given by 0.7788 into r, units henries per meter. Now we if we want to know the inductance expression for the total single phase line, means single phase transmission line. So means what? Single phase transmission line means there are two conductors. So what we do? Multiply this whole expression with 2. So that gives the inductance expression for a single phase transmission line. Okay, so that means 4 into 10 power minus 7 into log of capital D by R dash. So this is what finally written. So of inductance of one conductor, as we know. So again this one can be written as 2 into 10 power minus 7 log of, this is log base e, right? So if we write the above expression in terms of log base 10, so the above expression, same expression is given as 0.4605, okay, log base 10 d by r dash or r1 dash, and this is given in millihenries per kilometer. Okay, so this is the expression in terms of log 10 and millihenries per kilometer. So, and finally, summarizing again the previous points, internal flux linkages of a single solid isolated conductor is given by psi int, which is nothing but mu naught I by 8 pi, which is given by 1 by 2 into 10 power minus 7 I Weber turns per meter. Next, external flux linkages of a single solid isolated conductor is pi psi x is equal to mu naught I by 2 pi into log of capital D by R1, which so that is the external. Next, total flux linkages psi is equal to sum of the two, okay, psi int plus psi external, which we will get it as 2 into 10 power minus 7 I into log of capital D by R1 dash. Now, where R1 dash, we know that R1 dash or R dash 0.778 into R, okay, where R is the radius of the conductor, okay, given conductor. Next, then radius of the conductor in meters. Now, finally, inductance is given by this total flux psi by I, which is 2 into expression 2 into 10 power minus 7 log capital D by R dash. So that is a expression for the single isolated conductor. So as I mentioned already, if we consider the single phase transmission line, that means single phase two wire line. So inductance of a single phase two wire line means there are two conductors. Here, as you can see, conductor 1 and conductor 2. Here one conductor acts as a go conductor, other conductor acts as a return conductor. So here if you see conductor 1, whose current is I1, whose radius is R1, it is taken, and the return conductor current is I2, whose radius is R2. Here I1, okay, one conductor is acts as a go conductor, okay. So here I1 plus I2 is equal to 0, because one conductor is a go conductor and other conductor is a return conductor. So sum of the two currents is nothing but 0. So that means I1 is equal to minus I2. So that is a current in the two conductors, and if capital D is the distance between the two conductors, then this is given by, okay, like this. So this distance is given by from the center of the first conductor, this distance starting of the second conductor, D capital D minus, okay, capital D is the distance between the conductors from with respect to the center of the two conductors, okay. So then this distance with respect to from the center of the first conductor to the starting of the second conductor, that is capital D minus R2. End of the second conductor, that is capital D plus R2. Now, if we write inductance expressions for the two conductors as L1 and L2, L1 is given by 2 into 10 power minus 7 log of capital D by R1 dash, and L2 is nothing but inductance of the second conductor, 2 into 10 power minus 7 log of capital D by R2 dash. Okay, Now the total inductance. Okay, the total inductance of the circuit or loop inductance. It is also called like that. So for a single phase transmission line, the total inductance is given by sum of the these two. So which is given as L1 plus L2. So 4 into 10 power minus 7. Okay, because in the both terms 2 into 10 power minus 7 is a common. So if you take that out, so the expression will be, okay, 4 into, so 2 into 10 power minus 7 as common. So it becomes d by d square by r1 dash r2 dash, right? Okay, so if you take this to front, what it will become, this d 4 into 10 power minus 7 log of, if you write the 2 here also square, then it will become, if we assume there is a square here, then we have to write it square root here, right? So then it will become, this is a final expression. So now if both are same, radius of the two conductors are same, okay, then it will take it as r dash. Then the final expression for the single phase transmission line, 4 into 10 power minus 7 log of capital D by R dash, where R dash is 0.7788 into R, Henries per meter. As I mentioned this expression, okay, previously also, okay, the same expression. So if we look at small problem, here look at this problem. A single phase line has two parallel conductors 2 meters apart. The diameter of each conductor is 1.2 centimeter. Calculate the loop inductance per kilometer of line. So here clearly mentioned in the problem, it is a single phase line having two conductors, okay, and the distance between them is given 2 meters. Okay. Before that, first recall the loop inductance expression. Okay, this is an expression. Okay, 4 into 10 power minus 7 log base E capital D by R dash. Okay, so where D is a separation distance. So given capital D is 2 meter. Okay, then what is a radius of the conductor given, the diameter of each conductor given, so diameter by 2, this is 0.6 centimeter. So if we substitute 4 into 10 power minus 7 2 by 0.6, okay, so this D is in meters, so write this R, this is what, R dash. So where R dash is, we know that 0.778 into R. So 0.7788 into R.6. Okay. So substitute here 4 into 10 power minus 7 log of 2 by 0.7788 into zero point 0.6. Okay. This is in centimeters. So, but this 2 is in meters. So, this is 0.2. So, finally, 4 into 10 power, finally, L is given by 4 into 10 power minus 7 log base E 0.7788 into zero point 0.6. Okay. So, 10 power minus 2. 4 into 10 power minus 7 log 2. Okay. Get this 10 power minus 2 up. So, it will become 2 into 100. So, finally, the answer is given as, okay, this is the answer you can see here. So, this is for Henries per meter, okay. So after substituting, after calculating using calculator, we will get it as 2.42 millihenry per meter. So this is a problem based on single phase inductance calculation. Now continuation a small point. If we take a standard conductor, we know a standard conductor means there are number of small wires um, uh, which are um, wrapped together to get a large conductor. So under that we have different type of conductors. One of the type is ACSR conductor, aluminum conductor steel reinforced. So here you can see in the diagram, uh, this is a standard conductor with 7 steel strands and 24 aluminum strands. So aluminum conductor steel reinforced means inner strands are steel. Okay, outer strands are aluminum. So given there are 7 steel strands, inner strands, okay, inner side, and outer strands are aluminum, which are 24. Now here the total strands, the total number of strands is given by, denoted with capital N, 3x square minus 3x plus 1, where x is the number of layers. X is a number of layers. So that is how the total number of strands are calculated. Total number of strands are calculated. And the overall diameter of the stranded conductor is, okay, given as capital D, which is given by 2x minus 1 into whole brackets into small d. 2x minus 1 whole brackets into small d. Okay, again x is the number of layers and d is the diameter of the each strand. Diameter of the each strand means which is the same. Each strand having the same diameter. So this is how a standard conductor total number of strands are calculated and the overall diameter of that also calculated. Okay, that's all for now. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.